Hello everyone, I'm Meghamala, working as an assistant professor in Electronics and Communication Department, Institute of Aeronautical Engineering. Coming to today's topic, and today's topic is all about, it's a module 2, gate level modeling. So in the unit 1, that is module 1, we have discussed how HDL acts as a Verilog. So here in this module 2, we will see what all the gate level modeling consists of, and with some examples. So coming to the gate level modeling, we all know that Verilog is a built-in primitive like logic gates, transmission gates and switches, isn't it? So this Verilog, it has a library, and particularly coming to the gate level modeling, we construct or design the circuits in terms of the logic gates, transmission gates and as well as the switches. These are rarely used for design work, but they are used in post-synthesis world for modeling ASIC FPGA cells. So here, the designing part of the circuit diagram with respect to the gates, they are designed and they are used in the post-synthesis world for modeling of FPGA or ASIC cells. So what is this ASIC cells? ASIC cells are application specific integrated circuits. Okay, so for the application specific ICs or else field programmable gate arrays. So for this particular modeling of the circuits, basically we use this Verilog in terms of before the post synthesis usage. And gate level modeling, it exhibits two properties. So here we see two kinds of properties it associates. The first one is drive strength and the second one is delays. So what does the drive sense mean? The strength of the output gates. So here, for every circuit, for every combinational circuits that you consider, basically in terms of complex circuits, if you consider, there are some input gates and as well as the output gates. So here, the strength of the particular output gate is nothing but the drive strength. That means what? With how much of capability the output is acquired. So we all, it means that the strength of the output gates, and the output is strongest if there is a direct connection to the source. So here, this particular sentence is talking about the strength of the output driven gate. That means the strength is maximum, the output is strongest when if there is a direct connection to the source. If there is a direct connection to the source, then we say that the output gate, it gives the strongest, the driven strength is maximum. The strongest driven strength is observed at the output when if there is a direct connection, and the strength decreases if the connection is via a conducting transistor and least when connected via pull up or pull down resistor. And here the strength will become minimum when the connection is via the conducting transistor, when the connection is not directly but with respect to the transistors or else with respect to the resistors. Okay, with respect to the transistors or resistors, if you find if there is a connection with respect to the transistors or resistor, then the strength of the output gate becomes minimum, that is it decreases. So these are the two important points to be remembered when it comes to the drive strength. Okay, this is one of the property when it comes to the gate level modeling. And coming to the delays, already we have discussed what is a delay. Okay, what sort of delays we can observe in the gate level modeling or else in the data flow modeling. Okay, so if delays are not specified, then the gate do not have propagation delay, isn't it? The statement, it clearly says that when the delays are not specified, when there is no delay or else if though the delay is present but it's not specified, then it indicates that the gates don't have propagation. So there is no propagation, there is no transfer of the transfer of information has been occurred from the source to destination. So in that cases, they do not have any propagation, so the delays are not specified. If two delays are specified, if for example, if two delays are specified, that is one is around 10 and one is around 20. If it is delay 1, if it is delay 2. If two delays are specified, then one represents the rise delay and the second represents the fall delay. That means what? If this is the output, so this is a delay, rise delay for 10 nanoseconds and the fall delay for 20 nanoseconds. 20 nanoseconds. So here if you observe the delays of two, if you observe two specified delays, then one represents the rise delay and the second one represents the fall delay. If only one delay is specified, if you observe only one delay, for example 10 nanoseconds of delay, then both rise and fall are equal. That means what? In this particular, if you observe only one delay of 10 nanosecond, one delay of 10 nanosecond, then it means that this delay consists of one delay, that is rise delay of 5 nanoseconds and fall delay of 5 nanoseconds. Okay, if you observe both the delays, then one delay would be the rise delay, one delay would be the rise delay and the second one would be the fall delay. But if you observe only one delay, then you have to specify that it is very specific that the both will consist, that the rise and fall must be equal. And coming to the last point, delays can be ignored in synthesis. Already we have discussed in the previous module 1 what is synthesis, what is simulation, what are the system tasks and all. So when it comes to the synthesis, it is nothing but it is a procedure of converting the HDL language to the optimistic language, that is the description language of design into a optimistic. So the delays can be ignored in the synthesis. So there is no point of looking forward in when it comes to the synthesis. The delay won't be there in particular synthesis. Okay. Coming to the next point, here in Verilog, most of the digital designs are done at high level of abstraction like RTL. This RTL also we have discussed in the previous class. So what does this RTL talks about? RTL is Register Transfer Language. As I said we are discussing this RTL under gate level modeling. So this register transfer language is nothing but the transfer of information or the data between the registers. Okay, when you observe there is a transmission of information between the registers R1, R2, R3, then it is called as the register transfer language. So here this is nothing but it's a high level of abstraction. Okay, it all happens just because of the gates. The gates that you are considering, the information will be carried from one register to another register over the gates. However, now it becomes a natural to build smaller deterministic circuit at a low level by using combinational elements such as AND, OR gates. So here, so it is very natural to build a small circuits. Obviously, in the gate level modeling, particularly if you want to design any circuit, the basic gates that we consider is AND, OR. So this AND, by using this AND, OR gate, we can easily construct the low level of abstraction of the circuits. Okay, but when it comes to the high level of abstraction, then RTL, by using like RTL, register transfer languages, we will be achieve the maximum output. But when it comes to the limited output or else a limited level of abstraction, then it is obvious that using the combinational element and then OR gates are considered. Next, modeling done at this level is called gate level modeling, as it involves gate. So here, this particular sentence, it's very clearly talks about that though it is a small circuit, though it is a combinational circuit of a complex circuit, whatever it is, when you are designing a circuit with the gates, then that level, that modeling is nothing but the gate level model. Why? Because it involves the gates. You can see the involvement of gate can be seen at the input side and as well as the output side. And it has one-to-one relationship between hardware schematics and the Verilog code. So here in this gate level modeling, as it is a connection between the gates, so you see a relationship, one-to-one relationship between hardware schematics. That means you see a relationship between the different types of gates. Though it is OR gate, AND gate, NOT gate, whatever the gates that you are considering in that particular circuit, if it is a combination of OR gate, AND gate, NOT gate, then you see a relationship between these three gates and in the Verilog code as well. Okay, this Verilog code could be written in terms of gate level or else in the data level. And what are the keywords, how to write the syntax and all those things already we have discussed in the previous session. Coming to the point, supports a new basic logic gates known as primitives, as they can be instantiated such as modules and they are already predefined. So as I said you, this Verilog code, by using this Verilog code, we can relate the relationship, we can know the relationship, we can mention the relationship between the gates. Okay, how? With the help of these primitives. These primitives are nothing but the keywords, identifiers, okay, bitwise operators, operands, and all these things, all the lexical tokens that we have discussed in the previous session. These primitives consist of all such instantiated, how a particular keyword should be instantiated at the middle of the statement, or else at the beginning of the statement, or else at the end of the statements. All such things are nothing but the primitives. Already they are inbuilt in the Verilog. Already they are predefined in the Verilog. So the gate level modeling is used to implement the lowest level modules in design, such as multiplexers, full adders, etc. Verilog has gate primitives for all basic gates. So here the construction, coming to the examples. In the module 1, the last topic is about the design, examples of the design mechanisms. So in that particular examples, we have already discussed based on the gate level modeling how the circuits of multiplexer, full adder, half adder takes place. So here in this multiplexer, full adders and half adders, we have constructed using the gates, AND gates, XOR gates, AND gate, XOR gates and OR gates. The combination of sum and product can be seen with the help of this gate. So at the gate level modeling, it is used to implement the lowest level modules. These are the lowest level modules. That means they are very small modules that we can easily construct with the help of the gates, different gates. So this Verilog has gate primitives already present by default in already all the basic gates by default they are present in the Verilog library. Okay, by making use of all the gates, we will be constructing the combinational circuits which are very small circuits, that is multiplexers, full adders, half adders, decoders, encoders and so on. So Verilog supports built-in primitive gates modeling. The gates supported are multiple input, multiple output, tri-state and pull gates. So here the Verilog not only supports with the basic primary gates, but also it helps us to build a complex gates based on the primitive gate, built-in primitive gates. So these are nothing but the multiple input and multiple output, tri-state and pull gates. So these are the some specifications where the complex designs can be made. So in multiple input gates, we see the multiple input gates are nothing but like AND, NAND, or these are the basic gates as we all know. So whose number of inputs are 2 or more and has only one output. So here the name indicates that it is a multiple input gate. So multiple input gates means at the input part you can see 2 or more gates. Okay, 2 or more gates. But whereas in the output you see only one single output. The multiple output gates are buffer and NOT gate, whose output is 1 or more and has only one input gate. So when it comes to multiple input gates, for multiple input gates, we have many 1 or more input gates but single output gate. When it comes to multiple output gates, we see only one input but 2 or more than the output gates. So basically, the multiple output gates can be implemented by using buffer gate and NOT gate. Whereas here for multiple input gates, we see AND, NAND, OR, NOR, XOR gates. Next, the language which also support the modeling of tri-state buffer, including BuffIf0, BuffIf1, NotIf0 and NotIf1. These gates have one input, one control signal and one output. So here we see a different kinds of gates where it is BuffIf0. Okay, BuffIf0. Next, BuffIf1. And next, NotIf0. And next, NotIf not if 1. Not if 0, not if 1. Buff if 0, buff if 1. Okay, these are the special tri-state gates where it has one input, one control signal and one output. So these particular gates, they have only one input, one output and one control signal. These are nothing but the tri-state buffer. They include buffer input, buff if 0, buff if 1, not if 0, not if 1. And the pull gates are nothing but pull up, pull down with a single output only. So these gates, pull up gates and pull down gates, they are nothing but they have the output as only single output. Okay. Coming to the syntax. So here we have a syntax followed with the each type of gate with 0 delays. So here the delay is 0, and so it follows like this: AND, NAND, OR, NOT, XOR, XNOR. So here the instance name, and here is a port list. Okay, so here the instance name, whatever the gate that you are considering, the name would be mentioned, or is the name would be given by default here. And it is a port list. Port list consists of output ports and as well as the input port. Always remember that the output port list we have to declare first, and then comes to the input port. Then it is optional and is selection. So here this is an optional one. It's based on us. Whatever the gates that we are considering, this particular instance name is an optional and is selected. This bar, this is nothing but whatever the gate that you are comfortable that you are using. So whatever the gate you are using, that you have to consider. It's not mean that all the gates at a time to be considered, but whatever is needed for you, that gate can be mentioned over here. Particular gate can be selected from the Verilog primitives, but not. This is for another multiple. BuffNote is nothing but they have single input, single output and single selection, control signal, one control signal. Okay, so for BuffIfNote, buffer and not, this is how the same like the above one, mentioning the instance name, and this is the port list. And coming to the buff if 0, buff if not, same instance name, whereas here we see only one input and one output. So the input and output will be mentioned in terms of ABC. And coming to the pull up and pull down, instance name, output. Why? Because here there is a single output. We represent, there is a possibility of only one single output. So that's the reason in the port list we are mentioning only outputs. So this is about the syntax. Okay, coming to this particular slide, one can also have multiple instances of the same type of gate in one construct separated by comma. So as here in the previous syntax, we have discussed like AND, OR, XOR, and here instance name, right? And coming to the port list. So here this particular sentence is telling about that not only choosing one, we can also choose multiple instances of the same type of gate. So multiple instances, so that means multiple inputs are all the output ports, or multiple different types of gates we can choose, or else we can select by using comma like this. Instant one, this is output port of first instantiation one, and this is second for output port, third for the port list. So when you observe this particular instance one, you see here we will be representing with the gate name along with the port list. The port list, you are considering here 3 instances, right? 1, 2 and 3. So in the port list, you have to mention 1, 1, 1, 1, 1, 1. If it is output 1, 1, and if it is input 1, 1 and 1, 2, 1, 3, 1, 4, so on. Whereas here instance 2, you have to mention the output as 2, 1, isn't it? 2, 1 with the input port as 2, 1, 2, 2, 2, 3 and so on. Whereas here for instance 3, output 3, 1, 3, 2, 3, 3 and so on. If it is instance 4, my output have to write like this: 4, 1. My inputs are 4, 1, input 4, 2, input 4, 3, input 4, 4 like that. Okay. And end with the semicolon. Now, the gate level modeling is useful when a circuit is simple combinational, such as multiplexer. Multiplexer is a very simple combinational circuit, right? So the gate level modeling it is useful when you want to construct a single small combinational circuit like multiplexers, decoders, encoders, and so on. So a multiplexer is a simple circuit that connects one of many input to one single output. So what is a multiplexer? As we discussed in the previous classes, different types of multiplexers categorized. Multiplexer is nothing but many input, single output, right? So if it is 2 input, 2 output with one selection line. Okay, output. This is A0, A1. If it is 8 by 1, 4 by 1, 16 by 1. So here this multiplexer, it is a it is a simple circuit with many inputs, one of many inputs to the single output. So coming to the gate primitives. What does it gate primitives means? Gate primitives are nothing but they are predefined modules in Verilog. Already in the Verilog, they are present. So they are predefined modules in the Verilog which are ready to use. We can use when the time comes, we can easily we can easily grab it from this primitives, and we can make use of in the construction of the combinational circuits. Okay, so there are 2 classes of gate primitives. So here we observe 2 types of gate primitives. This is very important topic for the exam point of view. So coming to the first one is single input gate primitive. The second one is multiple input gate primitives. So what is single input gate primitive? Single input gate primitive is nothing but it has single input, one or more output. So here the name clearly says that single input gate primitives. So it has single input, one or more outputs. Single input, one or more output, one input. Okay. Next, the gate primitives are what? Not, buffer, not if, BuffIf. Also have a control signal. So, this kind of gates already we have discussed in the previous slide saying about this gates, particular gate primitive. This gate primitives, they have one input, output. But in some cases, we see there is single input, one control signal, and one output. Okay, so they have a control signal and they have one input. They may have 1 or 2 outputs. The gates propagates only if the control signal is asserted, else the output is high impedance state. So the gate, it just propagates only when the control signal is asserted. Like means when the control signal when it enables the inputs to propagate, then only the gate gives the output. Otherwise the gate goes to the high impedance state. We already discussed this about high impedance state and not don't care conditions. High impedance state and don't care conditions. So high impedance state is a saturated level where it does not give any output. So this condition we see when the control gate, when it doesn't enables to the input gates, then the output would goes maximum, or else the output would goes the don't care conditions. Okay. Coming to the examples. So here examples we have NOT and buff gates. By making use of the gate primitives NOT and buff gates. So these gates have only one scalar input but have multiple outputs. So NOT gate, one input, multiple outputs, and buffer also. Okay. So buff stands for buffer and transfer the value from input to the output without any change in polarity. So if it is 0, obviously it is 0. If it is 1, 1. So there is no change of polarity. Whatever the input is being given to the particular gate, the output you observe with the same. Whereas here NOT gate, if it is 0, the output would observe at 1. If it is 1, output is observed at 0. Okay. So NOT stands for inverter, which inverts the polarity of the signal at its input. So if my input is 0, I will be observing my output as 1. Okay, as it inverts the polarity. So 0 at its outputs will yield 1 and vice versa. So 0 at the output, when the input is 1, it yields 0 as output. When input is 0, it yields 1 as the output. Coming to the syntax, the representation of the particular gate with respect to the gate level modeling. Module is a keyword. Gate is a representation of a particular gate that you are making, that you are taking up. Input A and B and output C and D. And here these are the statements. The particular statement consists of, here I am considering 2 gates, buffer and NOT. So my buffer C, A, B, C is the output, A, B are the input. Whereas for NOT gate, D is the output, A, B are the inputs. And I am ending up my syntax with a keyword called end module. Okay, already regarding this keyword, module, end module, begin, we have discussed this. Module, end module. Begin, and, if, and while. Okay, all these you will see in the syntax. When you write the syntax, these are the keywords that are very important and prominent role they play in order to writing a syntax. Coming to the TestBench example. In this TestBench example, module TB TestBench. In the text, when you are writing a syntax in the TestBench, always remember that register we represent. Okay, register is a keyword where here it consists of the vector and the scalar components. So register representing with A and B, wire as C and D. C and D are the output. What is a wire? Wire consists of only 1 bit of data. Okay, if this is my input, my output is given to OR gate. So this is a wire which consists of either 0 or 1. So it is one of the keyword which is assigned in the continuous statement, continuous assignment statement. And wire C and D, integer I, okay, and the gates that you are using. I am using here A, B, C, D are the output. U of 0 is a gate, okay, buffer gate, or else it will be a NOT gate. And initial begin, okay, when it comes to the statements, I am beginning my statements. I am starting up with a keyword initial begin. A and B as 0. Monitor, I am displaying T, A, B, C, D time A, B, C, D. Obviously, will represent the delays. Okay, the delays will come across. The delays like A, B, C, D at the input and obviously at the output. And here the dollar and somewhere you will see the underscore. Okay, dollar and underscore are the keywords. Okay, they are the primitives. They have some specifications. Already we have discussed in the previous sessions about this. This will come across when you are writing a program or a syntax in terms of TestBench. Okay, and delays. A, B, C, D, time is nothing but the delay. And for, I told you, for is a keyword and while is also a keyword. So this for here, I is equal to 0, I less than 10, I is equal to I plus 1, begin. So it is random, A is equal to random. So for 1 bit of delay, we see when the input is 0, my output is going at, my input is taking right, just started at 1 bit of delay. Okay. If this is output, input, my output would be this one. So here you see a 1 input, 1 nanoseconds of delay. So that's how I've mentioned here. And B, A and B. That is, if this is a this is a B, output we'll observe like this. So totally 2 bits of delay we observe. And I'm ending up with this end, and this is with end module with end module. So this is about a TestBench syntax. Coming to the second examples, BuffIfNotif gates. So how can we write the syntax by using BuffIf and Notif gates? So BuffIf and Notif are the primitive gates. Those are for meant for buffer and inverters respectively. Okay, BuffIf is buffer input and Notif is inverters. So with an additional control signal to enable the output is available through BuffIfNotif primitives. So here when it comes to this BuffIfNotif, you will see a control signal. Okay. Control signal, if it is an input, output and control signal. So this control signal will enable the inputs in order to observe a particular output. So these gates have a valid output only if the control signal is enabled. So only if the control signal takes the initiation, only if it initiate the signal from the input, then only this gate is valid. Else the output will be high impedance. Okay, else the output will be, if the control signal is not initiated any signal from the input, then the output goes as high impedance. Next, there are two versions of this. One with the normal polarity of control indicated by 1, such as BuffIf1 and NotIf1, and the second one is inverted polarity of 0. So here in this BuffIf and NotIf gates, you see the output would be two polarities, with either if it is with 0 and 1. If it is with 0, we are calling it as BuffIf0, NotIf0. If it is 1, BuffIf1 and NotIf1. So the syntax goes like this. Module BuffIfNotif gates. This is a port list. So BuffIf is EAB, C is the output, AB are the inputs. And NotIf DAB, D is the output, AB are the inputs. And I am ending up with this as keyword and module. Coming to the test bench. So here in this test bench, again like the previous example, module BuffIfNotif gates in the test bench module, registers AB and wire is CD. So BuffIfNotif gate instance of 0. Okay, from 0, 1, 2, 3, how many instances you are considering? You have to mention here particularly separately. You can separately instance by using a OR symbol. So instance 0, CD, AB. My CD are the outputs, AB are the inputs. And initial begin. So how am I beginning my, I'm starting my program is 4 combinations using 0, 0, 0, 1, 0, 0, 0, 1, 1, 0 and 1, 1. Okay. So with the delay of 1 bit of delay. That is 1 nanoseconds of delay. So I'm ending up with the N module, N keyword. And now here in this, in order to observe, for the displaying purpose in the test bench, we have to, we will observe, right? So with how much of delay the output is carrying out. So in order to observe, in order to monitor, $monitor, C, instance A, B, buffer, BuffIf, BuffNot, and the delay mentioned with A, B, C, D. And I'm ending up this statement with N and with the whole test bench module with the N module. So this is very easy to remember and it's very important for the exam point of view. Coming to multiple input gate primitives. So what is this multiple input gate primitives talks about? Multiple input gate primitives are nothing but they includes AND or XOR, NAND and XNOR gate. These are the basic gates, universal gates, and they may have multiple inputs and single outputs. So previously we have discussed about single input primitive gates, right? And now we discuss multiple input primitive gates. So this multiple input primitive gates, they have multiple inputs and single output. So examples are here, AND or XOR gates. When you consider these gates, they need multiple scalar inputs and they produce single scalar output. So what does the word scalar means? Scalar is nothing but scalar primitives are there. They gives only 1 bit of information, 1 bit of data. So the data could be either 0 or in terms of 1. So these are the multiple scalar inputs. These gates, they may need, okay, they may need multiple scalar inputs and they produce only single scalar output. So here my inputs would be A and B. But I represent the output I may get either 0 or 1. When it comes to half adder, my inputs would be 2, A and B. When it comes to full adder, we are making use of 3 inputs, isn't it? So my inputs, when I compare with half adder and full adder, my inputs are more than 2. So, but my output is either 1 or 0, single scalar output. So, the first terminal in the argument list of this primitive is the output, which change and as any input shift. So, here the argument in the first terminal of this particular gates, if you consider the primitives of this multiple input gate primitives, we see the change in the input may shift based on the output. So here the syntax goes like this: module and or XOR gates, port list, output C, D, E, and input as A and B. So here I'm considering A and or XOR gates, right? So and or XOR gates with C as the input or output. Always in the port list we'll be mentioning the output first and then comes the input. So C as the input, A and B are the C as the output, A and B are the inputs. And for OR gate, D is the output, and for XOR gate, E is the output, A and B are the inputs. And I'm ending up with this AND module. So this is the basics syntax representations of the gates with respect to the input and the as well as the output ports. So when it comes to the test bench, the same follows like previous. Register A and B, and here wire C, D, E. Okay. Via C, D, E and or XOR. 3 gates we are considering it, right? So for each gate output is C, D, E. And XOR gate instance as 0. So here only I am considering only one instance as 0. If I consider more than once, I have to mention instance 1. Okay, instance 1s with the output 1, 1, input 1, 1, 1, input 1, 2, input 1, 3. Like that. So here in this particular example, I'm considering only instance 0. And then I'm beginning my statement as initial begin and then follows with the combination same 0, 0, 0, 1, 1, 0 and 1, 1. So this is a basic basic 2 inputs bit. When your gate is having only 2 inputs, then this is these are the combinations that we follow with a delay of 1 nanoseconds. And I'm ending up with the end. And initial begin in order to observe if for the display purpose monitor percentile T with different initiations A, B, C and so on, and this is the delay for output and as well as the input. In order to observe the delay in this for the same output and as well as the input, we represent with time $time, and I'm ending up with end and the end module. And coming to the NAND NOR XNOR gates. So these are inverse of all the above gates. So NAND gate is inverse to the AND gate. NOR is inverse to OR. And XNOR gates. So the design, the same design from above is reused. They are just for the interchange with their inversion version. So just to interchange. If you are getting, if my output and output is 0, 0, 0, 1. If it is my AND output. For NAND output is inverse of this AND. 1, 1, 1, 0. Isn't it? So interchange. The primitives are interchanged with their inverse version. So the syntax goes like this. Module, all the gates, port list with outputs and the inputs. And representation. The particular representation, particularly each and every gate represented NAND NOR XOR with outputs and as well as the input, with outputs and as well as the input, and ending up with the end module. And coming to the test bench, here the same register AB. Here my wire consists of C, D, E. Why? Because 3 gates I'm considering. So the output of each gate is represented as C, D, E. And the gate instance rate 0, only one instantiation we are considering. So that's the reason instance 0 with output and the inputs. And I'm beginning with the combination, same goes on 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0 and 1, 1. And I'm ending up with this. And in order to for display purpose, monitor with a delay and ending up with the end module. So this is all about the gate level modeling, single input and multiple output gates, and with the examples. Okay, with the basic examples we have discussed, and this is all about today's presentation. Thank you.
Like, share and subscribe. hit the bell icon for more updates.